Hello viewers, welcome back to our series of lectures on spectroscopy. Today we will start with a new spectroscopy that is called as electronic spectroscopy. The session is planned as follows, that is, to begin with we will try to ask ourselves what do we understand by electronic spectroscopy. Thereafter we will try to discuss about the potential energy curves for diatomic molecules and the selection rules which govern transition amongst them. Thereafter we will briefly bring in the Born Oppenheimer approximation. Thereafter we will see that how does this approximation help us devise an energy expression for the electronic energy levels of diatomic molecules, and then see that how does it translate into a suitable energy level diagram. Then we will see that the transition amongst these energy levels leads to what is called as a vibrational coarse structure in the spectrum there. We will talk about the origin of the structure and then see what kind of information is available from this spectra that I get there. Having done that, we will try to sum up what we do in today's session. Now, let us make a beginning by asking ourselves what is electronic spectroscopy. We know that spectroscopy in general refers to the interaction of radiation with matter, and the radiation belongs to different regions over there depending on the wavelength or the frequencies and all. Now, in case of electronic spectroscopy, we focus our attention onto the study of interaction of electromagnetic radiation in the UV visible region, and this interaction we study with the molecules, and then this interaction actually leads to the transition amongst the electronic energy levels of the molecules. So, that is the domain which we are going to work with. But the question comes up is, what are these electronic energy levels? Because to understand this, let us go back a little. Let us go back a little and see that when we talked about rotation spectrum, to understand that what we did was we considered the rotational motion of the molecules. We started by the rigid rotor, and thereafter we kind of moved on to non-rigid rotor and all. So, in the process we got quantized rotation energy levels which were characterized by a rotational quantum number J, and the energy levels were like this. They were separated by given by an expression there, and then there were the different energy levels there, and the transition among these energy levels led to the rotational spectrum. That means, basically the energy levels were coming as a consequence of the quantization of rotational motion. Thereafter, when we moved to vibration spectrum, here we considered the vibrational motion of molecules. We started by harmonic oscillators, then we moved on to anharmonic oscillators, and then again we got quantized vibration energy levels which were characterized by a new quantum number called as vibration quantum number, given a symbol as V, and that is a kind of expression we had. Here again we got a series of energy levels over there. There were the vibration energy levels, and the transition among this led to the vibration spectrum there. Now, in order to understand about electronic spectrum, we need to go back to the understanding of molecular structure. You will recall that when we talked about molecular orbital theory, we realized that the molecules have got molecular orbitals which spread over the whole molecule. Like in case of atoms, we got atomic orbitals which belong to the atoms. In case of molecules, we got molecular orbitals which belong to the molecule as a whole. Now, if you look further, these orbitals, they are with different energies. They correspond to different allowed electronic arrangements. That means, if I look at a molecule, say let me take a simple molecule, say hydrogen molecule ion or even hydrogen molecule. There are two nuclei, and there are electrons there which are distributed amongst around these nuclei there. Now, there can be different possible arrangements of electrons around the nuclei. Each of these arrangement corresponds to a given kind of energy, and that is basically what we mean by an energy level there. So, they are the electronic energy levels. Basically, they refer to different types of electronic arrangements around the nuclei in a molecule, and these are designated in terms of term symbols. Like we have in case of atoms, the different energy levels are characterized in terms of atomic term symbols. In case of molecules, we got molecular term symbols. We will not be spending time on that, but we presume that we have gone through this at some stage, and we know we are little familiar with that there are something called as molecular term symbols there. Okay. So, that is a kind of energy levels as they look like. Now, let us go further a little and then see that the kind of curves I was trying to show you, they basically are the potential energy curves. Let us try to formally define what exactly we mean by a potential energy curve. A potential energy curve basically, as it is stated here, refers to the plots of energy of the molecular orbital as a function of internuclear distance, that is given a symbol as r. What it means is, now suppose I am talking about a simple molecule, say hydrogen molecule or hydrogen molecule ion, that is the simplest one. Now, there are two atoms there. So, one hydrogen atom here, another one here, the two come closer. When they come closer, they form molecular orbitals. So, as they come closer, what happens to the energy? What happens to the energy of the system? That is what we try to understand when we talk about the potential energy curves there. Now, if you look at here, typically the potential energy curves are represented in terms of either the energy of the molecular orbital as a function of r, where r happens to be the internuclear distance there, or in sometimes what we do is we try to talk about the energy of the molecular orbital with respect to the energy of hydrogen atom. That means, how does it compare with that? Does it increase or decrease as a function of internuclear distance r here? Okay. Now, if you just look at these curves here, so this picture shows you the curves which are experimental curves are these ones, the black ones there, and the blue ones are the theoretically calculated curves, which are reasonably in good agreement with the experimentation there. Let us understand what exactly do they mean to us, why does it happen that we have curves of this kind. Let us analyze each one of them. We will spend time on talking about two curves particularly. One is your 1 sigma, one is your 2 sigma. 1 sigma is the so called, typically as we call it, commonly called as the bonding molecular orbital, and this is my anti-bonding molecular orbital there. Both of them are sigma here. Now, in order to understand these potential energy curves, we have to just have a relook at the energy expressions. The energy expressions, say for 1 sigma orbital or the 2 sigma orbitals, have the following expressions. We will not bother much about the expressions here, but what we have to understand here is this basically refers to the energy of 1s orbital of hydrogen atom, and this essentially is E square, r is internuclear distance. This j, k and s actually are different integrals, which are complicated expressions are there. We will not be concerned about it, but probably it will be worthwhile to talk something about the significance of these things. This integral j is basically concerns the interaction between a given nucleus and the electron density on the other nucleus, because we are talking about some kind of bonding here. Suppose there are two atoms there. So, when the two atoms are approaching each other, now this nucleus of atom 1 and there is an electron on atom 2. So, how does these two interact there? Some kind of a Coulombic interaction comes into play. So, this integral refers to this kind of an interaction. The second integral k basically deals with the interaction between nucleus and excess probability in the internuclear region. Let us understand that. What it means is the following. We know that suppose there are two hydrogen atoms are coming with their 1s orbitals there. When the two come together, these 1s orbitals overlap. When they overlap in the internuclear region, there is an increase in the electron probability or electron density over there. Now, when this electron density increases, so the interaction between a given nucleus and this electron density which is increased, that basically is manifested in terms of this integral called as k. And the third integral, that is s, is called as an overlap integral. That is very, very straightforward, that it concerns the overlap of atomic orbitals of the atoms as they are forming a bond there. So, all these three integrals s, j and k all are positive in signs there, that means in terms of the sign of one. Now, when I put their values into this expression there, so we find that there is some kind of a variation in the energy of 1s orbital or of 2s orbital as a function of r, and that is what basically is my potential energy curve. Now, let us try to see that how does the variation of energy as a function of r takes place, and what are the kind of phenomenon taking at that level. To begin with, when r happens to be infinity, at r is equal to infinity, basically our energy will be equal to that of the energy of a hydrogen atom plus energy of an hydrogen ion. What does it mean is the following. That means I have got two nuclei here, one is hydrogen atom here, one is hydrogen ion here. So, the two are far apart from each other, there is no interaction, energy is basically 0, so to say. As the two come closer, that means this is 1s orbital and this another one is there, as they come closer and closer, the energy changes come into play. And what happens is, as the distance between the two decreases, the two nuclei decreases, there starts accumulating electrons density in the internuclear region. That means, the two nuclei in the internuclear region, the electron density starts increasing, and because of that energy starts decreasing. So, you remember the curve, there is a decrease in that. Now, thereafter, that is the way we can probably look at it, that is, this was my one orbital here. So, this is what when I am referring to increase in electron density, that is what we are talking about. This is 1s orbital of one atom, this is 1s orbital of second atom. When the two come closer, they overlap constructively, and there is an increase in the electron density here. Okay. Now, at very low R, suppose we squeeze the two atoms very close, then what happens? What happens is that this electron accumulation does not remain very effective, number one. Number two, the internuclear repulsions come into play. As a consequence, the energy increases. So, and we have a profile as we saw earlier, that is, it starts decreasing, comes to minimum, starts increasing and increases like this. So, that is a typical potential energy graph, potential energy curve for sigma 1s orbital. Okay. Let us see what happens in case of sigma 2s. In case of sigma 2s, what you find is, again starting point is the same, that means at large r, the E is equal to E h plus, fine. But as we now decrease the value of r, as the two atoms are coming closer, but now there is some kind of a destructive interaction, there is no constructive overlap, there is a destructive overlap. As a consequence, there is a decrease in the kind of electron density in the internuclear region, rather it becomes almost 0, there is a node kind of a thing there. As a consequence, these two nuclei now are even more repulsive against each other, and as a consequence the energy starts increasing, and effectively speaking what happens is that this increase is sharper than that what happened in case of 1s orbital, and what we find is that for this orbital the potential energy is positive for all values of r, and that is a kind of curve we had. Okay. So, that is basically when we talk about potential energy curves, essentially it amounts to that how does the energy of a given orbital vary as a function of the internuclear distance. Okay. Let us move further and talk something about, let us raise a question again and find out what type of molecules show electronic spectrum. Here again we will try to go back a little and come back, that is, when we talked about rotation spectrum, we realized that a molecule will give a rotation spectrum if and only if it has a permanent dipole moment. That is the first, that is a kind of prerequisite we had for that. In case of vibration spectrum, the prerequisite was that any vibration must be accompanied by a change in dipole moment, otherwise it will not be absorbed, it will not be observed. And for the Raman spectrum, what we had was the molecule must be anisotropically polarizable. If the molecule is not anisotropically polarizable, then I will not be seeing the Raman spectrum there. But in case of our electronic spectrum, there is no prerequisite. Practically all molecules will show electronic spectrum. That means, no matter what kind of molecules we take, they will be giving you electronic spectrum. Okay. So, that is very different from all of the spectroscopies we have dealt with so far. Now, let us typically when you talk about spectroscopies, what we have been doing so far was, that is, what are the energy levels there, what is the energy expression, how does the energy level look like, and then what are the selection rules for that. And of course, we did talk about the prerequisites for a spectroscopy. The selection rules here happen to be as follows, that is, the certain rules like which concern the angular momentum, that is delta lambda is equal to 0 or plus minus 1, where delta lambda basically here is a quantum number which quantizes the component of total angular momentum along the internuclear axis. So, the selection rule tells me is that delta lambda should be equal to 0 or plus minus 1, that means it either remains unchanged or changes by 1 unit, and that translates into the transitions of this kind of thing only, that is, we can have a sigma to sigma transition possible there, or pi to sigma possible there, and pi and delta. But that means you have transition amongst these energy levels, but the transition amongst delta and sigma or phi and pi are not allowed. That means they do not confer to this particular selection rule for us. That is one. Secondly, very pertinent, very important selection rule for electron spectroscopy is that delta S is equal to 0, which means that is the electron does not change its spin during the transition. But what it means in simpler terms is, that is, the transitions can take place between either two singlets or two doublets or two triplet states, that is all. That means, or even more simply, what we can say is that during an electronic transition, the ground and their excited states must have the same spin multiplicity. That is the simplest way of putting it there. That means, we can have transition from singlet to singlet or triplet to triplet, but singlet to triplet is not allowed there. because that is a forbidden kind of a transition there. That means, and this rule actually breaks down when the molecules have got very heavy nuclei, but normally the kind of systems we deal with, we will be finding that this holds true. There is yet another selection rule here, that is, because when I am talking about homonuclear diatomic molecules, the parity of the state must change. That means, if I want to make a transition, it could be either from a G to U or U to G. You can't have a transition from G to G or U to U. So, that is the meaning of the parity being maintained over there. I am sure that you know about the parity here, because we talked about it when we talked about the molecular orbital theory there. Yet another selection rule is the symmetry of the sigma states does not change during the transition, or which means is that we can have a sigma plus transition possible there, or sigma minus to sigma minus. The other way around, that means plus to minus or minus to plus are not allowed there. So, they are the basic selection rules which become operative when we talk about the transition amongst the electronic energy levels there. Now, let us talk a little more about, because we basically the next requirement is that we must be able to talk about an energy expression for electronic energy levels there, and to get to that we need to kind of invoke Born-Oppenheimer approximation, and to do that let us try to have look at some data here. Typically what we done so far, earlier when talked about rotation spectrum, we realized that the rotation energy levels are very close, the difference is of the order of a 1 to 2 centimeter inverse. Then thereafter when we move to vibration spectrum, we realized the vibration energy levels are of the order of about 1000 to 2000 centimeter inverse away from each other. That means, the delta E values were about 1 k to 2 k centimeter inverse. Now, when you look at the electronic energy levels, we find that the separation is much larger. It could be about a million to 2 million centimeter inverse. It is much larger. Since the energy separations of different kind of energy levels is far apart from each other, that means, is about 1 to 2 centimeter inverse, about 1000 centimeter inverse and a million centimeter inverse. The Born-Oppenheimer approximation tells us that under such conditions, what we can do is that the total energy of the system can be taken to be equal to the sum of the 3 energies there. That means, the total energy of the molecule can be taken to be equal to the rotation energy plus vibration energy plus the electronic energy there. So, that is actually the consequence of our Born-Oppenheimer approximation. Now, if this be so, then what kind of energy level diagram would we anticipate? The energy level diagram will look something like this. That is, you will have ground energy states there, that means, this is my electronic energy level there, and then within electron energy level there are different vibration energy levels there, and within vibration energy levels there are different rotation energy levels there. You can see that schematically this has been shown that these energy levels are far close to each other, these are the vibration energy levels are farther apart and the electronic energy levels are still farther apart. It is not to scale, just to have you an idea about the way the delta E values are. Now, let us see that how does it translate into the energy expression which we are trying to look at. Now, if we ignore the rotation energy, which happens to be very tiny as compared to electronic energies, we can write that energy to be equal to sum of electronic and vibration energies there. As a consequence, we can write the expression to be that total energy to be equal to sum of electronic and vibration energies there, which actually translates into, if we just substitute the expressions for them, that means electronic energy we are taking as E electronic, and this is the expression which we kind of worked out when we talked about the vibration spectrum there. That is, this is a typical expression for my vibration energy levels there. So, the total energy will be equal to the sum of electronic energy plus the vibration energy there. Okay. So, that is a kind of energy expression we have. If this is an energy expression, what is a kind of energy level diagram? The energy diagram will look something like this, wherein this is my electronic ground state here, this is my electronic excited state, and within the each one of them there are the corresponding vibration energy levels there. So, V is equal to 0, 1, 2, 3 and so on and so forth here also. Now, you have to make note of two things over here. First, that the lower energy levels are indicated with the double prime, that is a matter of convention. That means, this will be V double prime here, this is V prime. Similarly, this will be E double prime and this is E prime here. Okay. So, the upper levels carry a single prime, the lower levels carry a double prime, that is one thing we have to keep in mind. And second thing we have to take note of it here is, that is, if you look at, just have a visibly if you look at it, these energy levels have got certain spacing there. But if we try to have a look at the spacing for that excited state there, we find that this spacing is slightly lesser, the energy levels are closer as compared to the energy levels over here. This is because of the fact that the anharmonicity is more for the excited state, which we have talked about when talked about the vibration spectrum there. So, but this has to be kept in mind. Okay. Now, if this is the energy level diagram, then we have to see that what kind of transitions are going to take place there. When you talk about the transitions, the possible transitions are as follows. That is, typically there is no restriction on the change in the value of vibration quantum number. That means, you can have transition from any vibration level to any other vibration level, because if you remember, for an anharmonic oscillator, the selection rule was that delta V to be equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on and so forth. That means, we can have any possible transition. But what you find is, if we start with a molecule in the ground state here, suppose this level happens to be the ground state here. If this is a ground state, we know that in the ground state, the molecule will be in the vibrational ground state as well. That means, it will be in the V is equal to 0 level. And we know that since the levels are quite far from each other, the population of V is equal to 1 and 2 levels are very, very small. As a consequence, all transitions which we will be observing, they will originate from V double prime to be equal to 0 level. When they originate from here, that means, that is why we can have transition from say 0 to 0 here, 0 to 1, 0 to 2, and so on and so forth. That means, all transitions will start from V double prime to be equal to 0 and then land into V prime to be equal to 0, 1, 2, and so on and so forth. Now, these transitions actually lead to a spectrum, and the spectrum looks something like this. That means, and this spectrum basically is referred to as a V prime progression. That means, we see that the transitions are starting from V double prime level equal to 0 here, and they are progressively getting into different V prime levels over there. So, this spectrum is typically referred to as a V prime progression here. Now, let us see further. What you see further here is that the transitions, this transition will be from here to here. So, this is going from V double prime to be equal to 0 to V prime equal to 0. This transition will be labeled as 0 0 transition here. That is what it is. The transitions are labeled as V prime, V double prime. This is a matter of conventions, we should be very clear about it. So, similarly, the next transition from here to here, this will be 1 0 transition. That means, it starts from 0, leads to 1, goes to level number 1 here. So, this will be 2 0, 3 0, 4 0, and 5 0 transitions there. So, basically what we have is that the spectrum basically is called as a band spectrum, because it constitutes a series of lines which put together is called as a band, and this band, as I mentioned earlier, is referred to as a V prime progression, because this is where the transitions are leading to. Let us have a look at one more very significant point here, that is, if we look at the lines here, we find that these lines are getting closer and closer as our value of V prime is increasing. Why does it happen? To understand this, let us have a real look at our V prime levels here. We find that the difference between V prime to V prime is equal to 0 to V prime is equal to 1 level is reasonably large, but as you go from level 1 to 2, this gets slightly closer, from 2 to 3 it gets still closer, and so on and so forth. That means, and this is just because of the anharmonicity term in the energy expression for the vibration levels that we talked about in the vibration spectroscopy. Now, that exactly is getting manifested in terms of the lines getting closer and closer. And one more thing which I mentioned earlier was that such a set of lines is basically referred to as a V prime progression there. Now, we got a spectrum. My question is now that suppose I wish to write an expression for the location of these signals in this V prime progression here. How do I go about it? What do they really tell us? Now, we look at say this transition here, say 5 0 signal here. The 5 0 signal essentially is originating from E double prime electronic, V double prime equal to 0, and is terminating at E prime electronic and V prime 5. So, that is my terminating energy level there, this is my starting energy level there. So, this is my E1, this is my E2, so to say, okay. Level 1, level 2, whatever. Now, suppose I want to talk about the expression for the difference in these energies there. So, what will that be? Now, if you look at here, just on the visually speaking, I find that the difference of energy of this level and this level can be seen as the difference in energy of from here to here. That means, this basically is my E prime minus E double prime. So, that is this difference here, plus I can move from here to here. So, that will be equal to V prime equal to 5 minus V prime to be equal to 0. So, that is the kind of difference I am going to get over here. So, that is the expression I am going to look at. Now, the expression will be something of this kind. So, in this expression basically we talk about the energies of the level at which the transition is leading to and the level from where it is starting from. And if we substitute the suitable values of the respective quantum numbers, then we find out the location of different lines in the spectrum over there. Now, we have got the spectrum, but how do I make use of it? What kind of information can I get from here? The information I get from here is there is plenty of information there. Suppose I can resolve the spectrum what I get there, and I get about 6 to 7 lines. Then this now, because I know that the origin of each line in terms of the energy expression I just shared with you. So, from that I can work out, suppose I got 6 or 7 lines in my spectrum, I can tag each line with the suitable expression from there, and then I do a little mathematics there and solve it out there, and from there I can get information about firstly E prime minus E double prime. I can just do some eliminations and try to work out this. That means, I can work out the difference in the energies of the electronic energy levels there. So, I did not know about the energy level difference there, I can get it from the spectrum. Secondly, I can get these 4 important parameters there, which is basically omega E prime, omega E double prime, x E prime and x E double prime. Now, I am sure that you will remember from your understanding of vibration spectrum that omega E prime is the equilibrium vibration frequency of the excited state, prime means the upper state here. This is the same for the lower state here, that is my double prime level there, and the corresponding harmonicity constants, say x E prime and x E double prime there. So, all that can be obtained by solving the simultaneous equation which we get as a consequence of the location of the experimental location of the signals in the spectrum there. Okay. Now, it looks very simple, that means we just get some sort of lines there which we can analyze and try to get lot of information, but actually the spectrum does not happen to be that simple, does not look to be that simple, does not come out to be that simple. The spectrum is little complicated for the reasons that because a given molecule may have number of possible states there as excited states. So, we just talked about only 2 levels, one the starting level there, the ground state, one was the excited state there, but suppose there are number of excited states possible there, which they are, in that case there will be large number of transitions coming there. Secondly, the transition from ground state to a number of different states, they will be allowed. We know that there are certain rules we talked about earlier, and as a consequence the spectrum will be accompanied by a band spectrum. Each sub transition will be accompanied by a band spectrum, and it will become a little difficult to analyze such kind of a spectra from there. Okay. Now, let us try to sum up what we have done so far. What we have done so far is that we started by defining what do we understand by electron spectroscopy. Thereafter, we explained the potential energy curves for diatomic molecules in terms of the energy of the molecular orbitals and things like that. Thereafter, we stated the selection rules for transition amongst the electronic states for diatomic molecules, and having done that, we explained Born-Oppenheimer approximation and described the energy level diagram under the approximation, and that is basically we focus attention only on to the diatomic molecules. And thereafter, we discussed the origin of vibrational core structure and information available from it. We talked about only the core structure because we ignored the rotation energy levels there. Suppose we consider even rotation energy levels there, the expressions get a little complicated, and we can think of the kind of fine structures coming into that, but that we will not be touching upon because that does not fall in the domain of this particular course there. Now, in the next session we will move further and then try to see, because what we have done so far is we have been able to just talk about where the signal is going to come, the position part of it. And you will remember that when you talk about spectroscopy, we try to talk about what is the location of the signal, and also the second important parameter is what is the intensity of that. So, the intensity of these signals, what are they going to be identical, are they going to be same or equally intense, or they are going to have different kind of intensities. So, that we will take up in the next session, and in that process we will talk about the Frank quantum principle, and we will see that how does that explain the intensities of the spectral lines in case of our electronic spectrum, the vibrational core structure of that. Thank you.